Hello everyone, welcome to this X-ray crystallography course. In this tutorial what I will do is I will try to address some of your queries what you have given through the feedback form. So one of the first queries some student have asked how to do the Miller indices or how to identify the Miller indices for a non-cubic crystal system. In fact, it is quite simple. You don't have to, the procedures for identifying the Miller indices or Miller indices, I mean directions in the crystal system or a Miller indices, that is a plane. You don't require a separate procedure for different crystal systems. The set of procedures given in this course is for any crystal of the form. So what I will do is to, since the student has asked that question, I will just write some of the procedures or some of the fundamentals. I will just once again I will write it on the blackboard, and then I will show that you can just easily mark the direction irrespective of the crystal systems and crystal planes and directions and so on. So that is the first question I would like to address. So first and foremost what you have to understand is every point within the lattice is uniquely defined by with respect to the origin of the lattice by a position vector r is equal to u dash a plus v dash p plus w dash c. This is a position vector. If the origin of the lattice lies on the lattice point, and if u dash, v dash and w dash are integers, then the point located by r must be a lattice point. So this is a very fundamental definition of a position vector. So if you understand this, so you will be able to realize that you can simply identify the position vector in any lattice form, in any of the lattices. So you can also rewrite this equation in multiples of u, v and w like this. So what we have written is you can also write this equation with the multiples of integers. The position vector can be written like this. So what I have written here is a vector between lattice points or between corners of equivalent unit cells plus a vector from the corner of the unit cell to a point within the unit cell at the position u, v, w related to the corner of the unit cell. So basically what you have to understand is you have to understand the position vector as well as lattice translation vector. You have to identify these two parameters, then it is easy for you to look at the general lattice. You can look at a general lattice of this kind. Let us consider let us consider this unit cell with the, initially we will assume this is an origin, and these are all the three perpendicular axis, that is a reference axis for identifying the direction of any kind. What we will do is So, direction to any unit cell or any crystal system, you must have studied in this course that it is nothing but the coordinates. You have to find the coordinates with respect to which direction you are interested in. For example, if you take this direction, for example, if you look at these two simple directions, so I do not have the coordinates of this is nothing but I have only in z direction, I do not have coordinates from any other axis. So, simply I can write like this. If you follow the steps what we have given in the course also, you will find that you will come to this. What I will do is I will just simply draw some arbitrary directions in this unit cell, then we will check our procedures what we have learnt in the course. So, the simplest directions what you can identify in any arbitrary unit cell of this nature, you see that this is 0 0 1 and 0 1 0 and this is 1 0 0 and this is again 1 0 0. These two are parallel directions. So, what you have to look at it, let the line pass through the origin of the unit cell and any point having the coordinates u, v, w, where these numbers are not necessarily integral. So, you do not have to worry about it, not necessarily an integral. For example, if I draw a direction like this, so you look at these two directions, we make sure that the direction is passing through the origin, and then how do we get this? Suppose if you look at the coordinate of this is 1 half and then 0, because there is no z direction. So, 1 half 0 is being written as 1 2 0. That means any fraction which comes, we make it as a, so that is what we do, right? We clear that fraction. So, let us write that point so that you will not forget. So, in these two cases, you take the coordinates like here it is 1 half and then 0 for this direction. So, you whatever the value you get for u, v, w, so you convert them into smallest integers by this. So, that is how you do it. So, suppose if you change the direction, suppose if you have some negative directions. So, what you have to do is either extend this unit cell to accommodate that negative direction. For example, this is a positive side, I can consider this as a negative side, I can extend this unit cell and then mark the direction, or mentally you can change the origin from within this unit cell to some other location depending upon the kind of direction you want to identify or determine. For example, if I will draw some negative direction in this unit cell itself, then you will appreciate that. So I have a two situation here. So this is about any fraction, so you know that now. So you can even write this coordinates like 1, half, 0, that you convert this into this, so that you will follow the similar procedure. What about this direction? So now I have mentally changed the origin from this to here. So this is my origin now. So this is the direction we are interested. So I am identifying this as 1, 2 bar 0. How do you do that? Because you have the coordinates, I have shifted the origin, so it becomes a negative. And similarly, you have origin shifted here for this direction. So write the coordinates 2 by 3, 1, 1. So basically the point is in a not in a half length, but somewhere 2 by 3. So since the origin is here, so I say that the coordinates is negative 2 by 3, 1, 1 for the other two units. So you convert that into 2 bar 3, 3. So like that you can identify the coordinates even with the arbitrary point on any line. Only thing is you have to just remember that where you keep this origin and then how your sign convention is. You have to make the reference axis clear in your mind, then you can always mark the direction without any problem, whether it is in plane or parallel to this axis, or it could be like 1, 1, 1 like this. So or it could be a fractional coordinates like this, or even the negative coordinates like this. Both of them you can identify, and then the procedure is same, but only thing is you have to just remember that origin where you shift. You cannot, as I mentioned in the previous case, like you can, for realizing the negative axis, you can always extend this. Suppose you consider this as a positive axis, you can extend this unit cell and then again draw this, or mentally you change the origin, and then with respect to origin you define a reference axis, whether it's positive and negative, and then follow the finding out the coordinates, and then if it is a fraction you convert them into a smallest integer and put them in a square bracket. So that is a standard procedure. So now what I have not even defined what crystal system this is. This is just done, this exercise is done on an arbitrary unit cell. So similarly you can practice any system till you become comfortable to identify this, the direction in any arbitrary unit cells. So similarly we will look at some of the examples on the planes. So, what normally we do for identifying the Miller indices of a plane, we always try to orient the plane or make the plane inclined to the reference axis. Wherever the reference we have kept, then we incline the plane into the 3 axis and then try to find out what are the intercept that plane is making on each reference axis. So, finding out the intercepts. So, what we have I have taken again an arbitrary unit cell where you have this axis, reference axis A, B and C. So, I have drawn a plane. You can see that this plane is identified as a 4 2 1 plane. If you go back and look at the procedures what we have already done, you can see that each axis has got a different divisions. So, basically we have just taken the intercept of we have arrived at this Miller indices by calculating the intercepts. But before that, what I would like to discuss with you is, suppose So, I am trying to explain why we use certain procedure to, I mean this particular procedure to arrive at the Miller indices, because as I just mentioned before, if you want to look at the plane, if you want to identify with reference to this reference axis A, B, C, we always look at the intercepts. And in fact, the orientation of the plane might be giving the actual distance measured from the origin. You can always use that actual distance from the origin. But the problem comes is when you have a plane which is parallel to any one of the axes, then that plane will never make an intercept with that axis. So, that is why the reciprocal of the whatever the intercepts you get, that comes, because 1 by infinity is always, you can make it as 0, and then you can put them into a curved bracket. So, that is the point you have to understand. Otherwise, whatever the actual distance measured from the origin, for example here, that could be a straightforward case, but then in order to avoid this a parallel plane conflict, because they will never make a particular intercept value with any of the axes. So, that is why the Miller indices are defined as the reciprocals of the fractional So, that is why the Miller indices are defined as the reciprocals of the fractional intercepts which the plane makes within the crystallographic axis. So, now I have not again taken any particular system of crystals, but it is shown in an arbitrary plane. But now you can see that as per the procedures laid down in the course, we will look at what are the axial lengths, So, you have if you look at this diagram, the axial lengths are 4, 8 and 3 in units, any units here. I have not put any particular units. So, the intercept length is you can look at 1, 4 and then 3. So, fractions of this is 1 by 4, 1 by 2 and 1. So, if you make it in smallest integers, then this is 4 to 1. So, that we put it in a bracket. So, this is how the Miller indices for a plane is identified. So, this is the same procedure what we have followed in the lecture what you have seen. All that I have now shown is some of the arbitrary crystal system. You can identify this and then you can practice on more different unit cells, then this point will be much more clear. So, what I will do now, so some of the points which you have to remember when we look at the Miller indices of the crystal systems. The planes whose indices are negative of one another are parallel and lie on opposite sides of the origin. For example, 2 1 0, 2 1 bar 1 0. They are of the same plane but with opposite. They are parallel planes but with the negative indices. The planes NH, NK, NL are parallel to the planes HKL and have 1 by nth the spacing. So that is the, you can have some rough idea about how dense planes they are. Miller indices of one set being a multiples of those of the other, thus the same plane belongs to the, for example, 210 set and the 420 set. They are all parallel planes. For example, these two will have the 210, for example, the 210 set form every second plane in the 420 set. So it will be a parallel plane. So some of the things you have to remember, but another important thing is in a cubic system, what you will have is the plane normals are always perpendicular to the plane. That means the direction and the plane are mutually perpendicular in the cubic system, but in other systems it need not necessarily true. That is the only difference. For example, in cubic system, if you take 111 direction, that will be perpendicular to 111 plane. Similarly, for all the Miller indices. But in other crystal systems, it is not necessarily true. It will be something different. So that is the only thing you have to remember. Otherwise, these points are still valid. So another important point is to have about this Miller indices is the planes of large spacing have low indices and pass through a high density of lattice points, whereas the reverse is true of planes of smaller spacings. So you can have some idea about just looking at the Miller indices. So you can have some idea. What I will do is I will just draw the lattice so that that is useful. You can identify them by just looking at the lattice. Suppose if I define this lattice like B. Suppose if I define this lattice and the lattice translation vector like an A and B, so suppose if I want to identify this kind of a plane, this is 1 1 plane because we are talking about this is 1 1 plane because we are talking about 2D. So in 2 dimensions, so it is 1 1. Suppose if I extend this lattice further, so what I have done here is, suppose if I looking at this spacing of this nature, so it is like 4 1 bar. Why 1 bar? I have changed the direction, and you see this is a 4 unit, 1 2 3 4, so it is 4 1. Suppose if I extend this lattice further like this, so this is 1 0, because it is only one direction, so the other direction is 0 intercept, I mean it is not connecting the other direction, so it is 1 0. Suppose if I extend this further, I can show few more. So what I have tried to show in this lattice, you see that the low indices plane have the greater spacing. What I have just written here, I have just shown in the schematic. So the low index plane have higher spacing compared to the high index plane, like this 1 3 4 1 1 0 and so on. So this will give you an idea. By looking at the Miller indices, you can imagine the high indices plane will be less, have the less interplanar spacing. So with this I will conclude this session of the Miller indices and directions. I hope you have some clarity on this. You just do a practice on some of the exercises I have demonstrated. Now I will move on to the next question the other students have asked, to explain the Bragg law much more elaborately, connecting the reciprocal lattice concepts. So what I will do is I will redo that exercise on the board, then we will discuss. So now look at the diagram. You have already seen this twice. In fact, once I drew it for the tutorial class, and the other time you must have gone through the lectures. So the question is, can you explain the diffraction phenomena relating reciprocal lattice a little more elaborately? Okay, so that's a concern from some of the students. So what I have written here is the reflecting sphere is also called Ewald sphere. So it is a concept to it's an imaginary concept again, like we stated in the lecture, to connect the reciprocal lattice and the Bragg law. There is a link between a reciprocal lattice and a Bragg law. That is also you can use it as a, I mean via media to understand the diffraction phenomenon. So what happens is, this is an you assume that this is an incident beam which is falling on a crystal, and this is the diffracted beam, and this is the undeviated beam or transmitted beam. This phenomenon is the same whether the incident beam is an electron or X-rays. Diffraction principles are the same. So what you have to look at this is, here what I have drawn is G is the reciprocal lattice vector. That is what OP, what I have written, the reciprocal lattice vector G. And you can, the magnitude of G is 1 by D. D is the interplanar distance. And if you look at the angle of X XPO is right angle, that is you have XPO is a right angle here. XP must be represent the trace of the plane, that is XP, the trace of the plane is HKL, and it follows that OXP is equal to theta. Where is the theta here? OXP is theta here, again the theta is here, the angle between the diffracting plane and the incident beam. So, from the triangle OXP, this is a triangle. So, you have sin theta is equal to OP by OX. How do we define the OP here? OP is here, it is G is nothing but 1 by D, and OX is nothing but 2 by lambda. This is 1 by lambda, so this is 2 by lambda. So, we have written like this. If you rearrange this, then you get the standard Bragg's law. Okay. So, if you look at this simple geometrical aspect, then it may look more mathematical rather than the concept. But then what if you look at the schematic little more closely, I have just drawn the spots to the background of this diagram, and this the circumference of this sphere is cut through only 2 points here, but this is a lattice, an imaginary lattice which goes, it is an infinite imaginary lattice. But if you look at the sphere, it cuts through only 2 points, not the other points. Okay. So, that is another thing you have to understand. But now, what we have done, we have taken this reciprocal lattice vector, this vector which is nothing but 1 by D, those things are there. So, now you see that this is the direct beam and this is the diffracted beam. So, the distance between the direct beam and the diffracted beam we define as reciprocal lattice vector or diffraction vector, we can also call it as a diffraction vector. Okay. Now, to understand this phenomenon little more clear, from this geometry what we have done is, when the lambda is equal to 2d sin theta, when the lambda is equal to 2d sin theta, then this geometry is valid, right? Or other way, you can say that when this condition is satisfied, when the lambda becomes 2d sin theta, then the diffraction takes place, because the sphere does not cut through any other point but only this point. That means, whatever you see as a diffracted beam in an experiment has to obey this. That means, the wavelength of the incident radiation should be satisfying this condition. Then what happens when you have the, or it could be like this, n lambda. So, it could be an integral multiple of lambda. If it is of this nature, then what happens, the constructive interference takes place and which gives rise to the diffracted beam. Okay. So, if you look at the lecture notes much more closely, what clearly shown in the parallel planes of like this incident beam, and then this is diffracted beam like this. So, if you assume this like this is having some lambda, particular lambda, it will have some particular lambda, but when it is reflected that side, when this condition satisfies, then that incident is called a diffraction, that phenomenon is called diffraction. That clearly demonstrated with this diagram. Unless the Ewald sphere cuts through perfectly the reciprocal lattice vector, then you cannot call it as a exact diffraction. Then you may ask why we confuse this with this diagram when we can understand this with this kind of a parallel plane, and then it is and the diffracted beam, and whether they are in the same phase, then the constructive interference takes place and or not. The idea is, suppose if you have this Ewald sphere as a reference, when the Ewald sphere exactly cuts this, then it is exact diffraction or exact Bragg condition. The theta is perfectly a Bragg angle. It is on, otherwise you can always call that, you can have a spot like this which is very close, or somewhere in an imaginary, not this particular lattice, imagine that you have a spot which is here or spot which is here. Sometimes it may come, a reflection may come, that will be called inexact Bragg condition. So, this is the distance is measured as a deviation parameter called S. So, this is positive S and one is negative S. So, deviation parameter, that is not an exact Bragg condition, but it is a deviation from the Bragg condition. So, in order to conceptually capture the idea of where is this exact Bragg condition is met, and this Ewald sphere construction really helps. So, wherever I have just drawn only a few reciprocal lattice points for the reference. Suppose you imagine that whatever the spot it cuts through in this lattice, so suppose if you assume that it cuts through so many points exactly on this, so you will see highly dense diffracted spot in the diffractogram, or in even if it is an electron diffraction, you will see it in the screen lot more spots. So, this is a sphere, so it is a 2D projection here. So, you assume that it is a 3D if it cuts through the 3-dimensional lattice. So, wherever the surface cuts through the exact lattice positions, so many spots will be appearing in a back focal plane or a diffracted plane. So, what you have to understand is, suppose if this is away from this sphere, whether this way or that way, your exact Bragg condition is not met. So, you will not have a peak intensity of the diffracted beam. So, you will have a very weak intensity of the diffracted beam. So, this can also be visualized in this form. For example, here it is a direct beam K naught, a diffracted beam is K. So, you have this diffraction vector G. So, vectorially we can show this as G is equal to K minus K naught. This is another way of showing a Bragg law in a vectorial form. So, So, there are two things you have to keep in mind. One is a geometry, simple geometry. The other is the physics behind this whole phenomenon. Okay. So, both are imaginary concepts, but then it helps to realize that what do you mean by exact Bragg condition, and how the the diffraction really connects the reciprocal lattice. So, this is the Ewald sphere concept is a link between a Bragg law and a reciprocal lattice. So, that way it is most useful. So, another important point you can relate, if you look at the X-ray diffractogram or XRD data, you normally get very few number of peaks as compared to electron diffraction pattern. In a single crystal pattern, you will see lot more spots. That is because the lambda is too small in an electron in an electron beam as compared to the X-ray wavelength. So, that means the Ewald sphere is too big. The lambda becomes smaller and smaller, then your sphere becomes very big, then it will cut through, the surface of the Ewald sphere will cut through n number of points. So, you see lot more diffraction spots in an electron diffraction as compared to X-ray diffraction, which gives very few diffracted spot or peaks. So, that is another way of visualizing this diffraction phenomena using this Ewald sphere, where it is very convincingly you can appreciate the usefulness of this diagram. So, look at this Bragg law by thinking about two aspects. One is geometry, another is you can just look at by simple vector process or vector algebra, or you can just think of some complete physical phenomenon. You have to put all together, then your understanding of diffraction will be much better.